Good day, we are Group 10, students from Mapua University, and our project is titled Traffic Flow Simulation using agent-based model in NetLogo, developed in NetLogo. Traffic congestion is one of the most critical challenges in urban areas today, not just in the Philippines but globally. It affects not only travel times and economic productivity, but also contributes to increased air pollution, energy consumption, and stress levels. Our objective in this project was to simulate basic traffic behavior at the microscopic level using an agent-based model with NetLogo. By representing each vehicle as an independent agent, we can observe how local interactions between cars affect overall traffic flow. In the real world, traffic systems are influenced by several interdependent factors: the number of vehicles on the road, their speed, acceleration, and braking behavior, lane discipline, and reaction times of drivers. For example, a single student brake can trigger a wave of slowdowns behind it, a phenomenon known as phantom traffic jam. In this simulation, we attempt to replicate similar dynamics in a simplified environment where we can control these factors through input sliders. This model, though basic, provides valuable insights into how traffic congestion forms and how it can be reduced or managed. Through parameter adjustments, it reflects real-world issues such as delayed driver reaction, insufficient spacing, and inconsistent driving speeds.
Okay, so here's our simulation model. The white road, as you can see here, is the in the middle represents a straight road, while the colored car icons, or which is called turtles, are the vehicles. The blue cars represent the regular vehicles, while the red or the pink car is a sample vehicle highlighted for trafficking its behavior. For the sliders, these sliders allow you to adjust the key simulation parameters. Like for example, the number of cars. It controls how many cars are placed on the road. More cars is equal to more congestion risk. For the acceleration and deceleration, it allows you to adjust how quickly a car speeds up when the road is clear ahead, and the deceleration, how quickly a car slows down. For the button setup and go button, the setup button initializes the road and places the cars with random starting speeds and positions. For the go button, it starts or stops the simulation loop when running. Each car continuously checks if the car is ahead. If yes, it accelerates. If no, it accelerates. For the car speeds, the red car's speed, this graph shows the real-time changes in car speeds over time. Okay, let's run the simulation. For example, the red line is the speed of the red car or the pink car. The green line is the maximum speed among all cars, while the blue line is the minimum speed among all cars. So what's happening in this simulation? Each car is autonomous and decides how to move based on what's directly in front of it. If a car is too close to another, it slows down to avoid collision. If the road is clear, it accelerates toward a speed limit, and this interaction creates a realistic traffic behavior such as smooth flow with few cars, jams and stop start motion when there are too many cars, or high deceleration. So our model uses a microscopic modeling through NetLogo's agent-based simulation framework. Each vehicle is modeled as a turtle agent, on a one-lane horizontal road, represented by a white colored patches in the center of the world. This is called the World in NetLogo app. So for the code, the code begins by defining global variables such as the speed limit, minimum speed, and a reference to the red car. Each car also has a speed attribute which is unique to that turtle. The setup procedure clears the environment, sets road colors, and creates car agents with random positions and speeds. A recursive method called separate cars ensures no two cars spawn in the same patch. The go procedure is the core of the simulation. It executes continuously and updates each car's speed and position based on the presence or absence of a car ahead. The car either slows down by subtracting and the ace deceleration value from its speed or speeds up by adding the acceleration value. Speed values are the cap between the defined speed min and speed limit. The red car speed is tracked visually and data is plotted in real time. The simple rule-based behavior procedures complex group dynamics similar to what we observe in real traffic.
For our simulation, we simulated with an average number of cars. In this case, we used 23 cars, and we observed that how the red car behaves as it travels around the simulation. For the first trial, the red car accelerates until it encounters a vehicle in front of it, and then it decelerates to avoid collision. Once that the traffic has moved, it then begins to accelerate again. This creates a sawtooth pattern in the red car's speed graph, reflecting a stop-and-go nature of the traffic, creating a phantom traffic jam. If the number of cars are increased, we observe that the frequent that cars brake, the more traffic it congests, and thus lowers the average speeds. If then deceleration is set too low, cars fail to slow down in time, leading to simulated overlap or traffic breakdowns. Through the trials, we are able to see how even small changes, like the concept of Monte Carlo, changes in driver behavior or vehicle distance can lead to significant changes in the traffic flow efficiency.
To conclude, our simulation has demonstrated that even a simple agent-based traffic model can reveal important insights in how congestion emerges. This model shows how traffic flow is not only dependent on road infrastructure, but also is significantly influenced by the behavior of individual drivers. The simplicity of our model is both its strength and its limitation. While it effectively demonstrates the emergence of traffic patterns, it lacks elements such as intersections, traffic lights, lane changes, or multiple road segments. In the future, the simulation can be extended to include multi-lane traffic and overtaking behavior, smart car behavior with adaptive cruise control, real-time traffic signal coordination, and external factors like weather or road obstructions. Ultimately, our project serves as a stepping stone towards more comprehensive traffic analysis and contributes to the understanding of urban mobility systems.
Okay, thank you very much for listening. Again, this group and I hope you learned something from our simulation model.